So the, now we will explain how to model failures in our system. And in this course we will look mainly at two failure models. The first one are crash stop failure and the second one are byzantine failure. So a crash stop failure is something that will happen on a process. When a process is crash stopping, it just stops working. You can imagine it as a process where you cut the current, the electricity to the process, and it just stops executing your program. And while a byzantine failure is an adversary that compromises your process, and your process starts to behave as the adversary wants. So in our execution model, we have that we model crash stop failure with the event crash process J. And when this event happens in our execution, we have that process Pj does not execute any more local computation step. So in our execution, after crash Pj, we have that we cannot have a step execution J. And this model, if you think a bit about it, the fact that process Pj crashes and never answer anymore to our algorithm. So when we want to model and to create an algorithm that is fault tolerant, we have to imagine that this algorithm can run in an execution where a process can crash. And remember that, notice that the definition of execution that we have done until now is independent of the algorithm. So it runs on every possible algorithm, and the code of your algorithm is actually hidden behind the things that you do when you have a local execution step. And this is the power of modeling things in a formal way, because the theorem that we have shown in the previous video, the one that says that no algorithm can learn the execution of the system because of the indistinguishability, it's really powerful, because by discussing execution we know that that result has to hold for any algorithm, because the indistinguishability holds for any algorithm. And then we have the Byzantine failure, and we model it as Byzantine Pj, the event beats Pj. And after this event, we have that process Pj behaves in an arbitrary way. So it means that every time Pj executes a step, it does not follow anymore the automaton of process Pj, that is our distributed algorithm. The automaton is implementing our distributed algorithm. And we have that Pj is not following anymore our algorithm, but an algorithm that can be designed by an adversary. And of course, we have that a Byzantine failure is stronger than a crash stop failure, because you have that a process that failed in a Byzantine way can also exhibit a behavior that is equal to the crash stop failure, because it's possible that it goes in a local automaton in which for each local step it never sends any more messages, and this is equal to seeing as if the process crashed. And we say that a process is correct if it does not experience any failure. But the trick with distributed computing is that we do not know who is correct and who is not. So we have to design algorithms that work even if they are uncertain about the correctness of other process. And usually what we do is that we indicate with letter F the maximum number of processes that can experience a failure event in an execution. And usually we want to bind F, and we want that it cannot be larger than n-1. So we have that we need at least one correct process. And this is trivial, because if we do not bound the number of failure, then any possible algorithm we can have an execution in which the first n events are all crash, in which you just crash one process after the other, and then you cannot execute anything. So usually we bound F to be more than n-1, and we will see that for a lot of interesting cases we need that F has to be more than half of the process, or in case F has to be less than half of the process, or in the Byzantine case has to be less than 1/3 of the process. But we will explain it in the future lecture why this is so. And we never do assumption on when a failure event happens, and this is because, remember, the events are decided by an adversary, that is the scheduler, and the scheduler can put the failure any way it wants. So if the worst case is to put the failure at the beginning for your algorithm, it will put the failure at the beginning. If the worst case is to put the failure a bit before your algorithm output a result, it will put the failure there. So you never imagine that you can have control on when something fails. And those are two homeworks. The first one is to model the loss of a message as an event for the execution, similar to the local execution step, to the crash event, and to the delivery of message event. The second one is to formally prove the agreement impossibility that we have shown in the introduction, and is the one in which Alice and Bob, they have to decide on which time to attack.